Alright, in this video we're going to think about what this integral represents, explain what that integral represents, and then evaluate it over this region that's described here. Okay, so first of all we want to think about what this integral represents. So remember that all of these double integrals are really Riemann sums. So I'm just going to write that Riemann sum that this one would represent. For this one, notice that we just have dA here. So we're really just adding up all of the delta A's. And so if you remember what the delta A sub k represented, those were areas of all the little pieces in our partition. So we're adding up all of the areas of the pieces in our partition of R. So what this would represent is really just the area of R. Another way to think about what this integral is to think about the function that we're integrating as just 1. And in that case, we end up with a slightly different Riemann sum. So we've got 1 times all of the areas. So if we think about this in terms of dimensions, for this one, we might have a region R down in the xy plane, and then our height function would be given by 1. So what we would really end up with there is the volume of a cylinder whose height is 1 and whose base is that region R in the xy plane. So in this case, this would be a volume, but numerically this area and volume would be the same. If we need to think about dimensions, then maybe they don't have the same dimension. Area would be measured in square units and volume would be measured in cubic units. But if we're just interested in the numerical answer here, numerically those two things are equal. All right, so now that we understand what this integral represents, let's go ahead and evaluate this integral over the region R that's described. So the first thing I need to do is draw that region R. And I'm just going to draw that in the xy plane. Okay, so I've drawn all of the curves here, and one thing that sometimes students have a hard time with is that they're focused on the incorrect region. So you need to make sure that the region that you're focused on is actually bounded by all of these curves. So if I look at that carefully here, I've got a region down here in the 4th quadrant where I've got the ln function on the left side, the line x plus y equals 1 on the right side, and then y equals -2 on the bottom. That's the only region that's actually bounded by all 3 of those equations. Sometimes students focus on a region perhaps over here, but then you would be inferring the y-axis as a boundary, or maybe the x-axis even as a boundary, but neither of those is described as a boundary of the region. So that's not the correct region. Okay, so once we've decided what our region is, now we just need to set up the integral. So I need to think about whether this region is x simple or y simple or neither or both. When I go through the region in the direction of increasing x, I'm always entering through the logarithm curve and leaving through the line, x plus y equals 1. When I go through the region in the direction of increasing y, I'm always entering through y equals -2, but sometimes I leave through the logarithm curve and sometimes I leave through x plus y equals 1. So this region is x simple, but not y simple. So I'm going to set this up first with a dx on the inner integral. All right, so when I set this up with dx on the inner integral, I'll need to solve my equations for x. So my logarithm curve here, when I solve that for x, I will get e to the y equals x. And when I go through the region in the direction of increasing x, that's where I enter, e to the y, and then I leave through the line x plus y equals 1, so I'll solve that for x. And the function I'm integrating here, if you want to just write a 1, you can do that, or just write dx here. And then my dy limits of integration, I need to think about what y goes from, think about projecting that region back onto the y-axis and looking at the minimum and maximum values. So that'll just go from y equals -2 to y equals 0. So the region is not y simple, but I actually can set this up with dy on the inner integral if I want to. If I do that though, I'm going to have to split the region where it switches from going through one curve along the top to the other. So I'll have to split that into 2 separate integrals. I'm going to go ahead and set it up that way. Okay, so when I set this one up with dy on the inner integral, when I go through the first region on the left side here in the direction of increasing y, we'll enter at y equals -2, and then we'll leave through the logarithm function, solve for y. And then I need to think about the x limits of integration. So I would project that up onto the x-axis, and I need to figure out the x-coordinate of that point where the logarithm function intersects the line y equals -2. So I'll just do that right here. So we get that that point is e to the -2 comma -2. So our x we'll go from x equals e to the negative 2 to the place where we stop going through that curve. So that's at x equals 1. And then for our second integral, we'll go from x equals 1 to whatever this intersection point is over here, where x plus y equals 1 intersects y equals negative 2. And in that region, y will enter at y equals negative 2, and we will leave through the equation of the line x plus y equals 1, solve for y. Okay, so I can actually do that one. I just have to split it into two separate integrals. So if I'm going to choose which way to do it, and I'm not forced to set it up both ways, or if I need to evaluate one of them, I would choose to evaluate this first one. It's much easier to evaluate. So I'm just going to scroll this up and go through that integration. All right, so once I integrated with respect to x, and then I plugged in my limits of integration, and then I integrated with respect to y, be careful about this. A lot of times students just neglect plugging in 0, but on this one especially you need to be careful, because when you plug in y equals 0, you don't just get 0 for that entire function. E to the 0 is 1, so you need to be careful about that when you plug 0 in here. Okay, so I've gone ahead and finished the integration here, and I got 3 plus 1 over e squared, so that is just a little bit bigger than 3. And remembering that my answer represented area of the region, we can look up here at the region and think about whether the answer is reasonable. Our region is not quite a triangle, but is pretty close to the shape of a triangle, and so you could find the area of a triangle with about those dimensions and use that to verify that this does seem like a reasonable answer.